All right. Okay, hi everyone. My name is Mihai Donțu. I work at Bitdefender, and I'm currently involved in a commercial security product using the introspection features of Zen. It's that commercial part that Andy's trying to do without, probably because I haven't delivered a build supporting Zen 4.9 in a while, even though I promised it. All right, this is a third presentation in a series. Didn't intend it to turn that way, but here I am. For the past year or so, we've been hardly at work. We've been working on improving the performance of our product. And we were thinking, okay, what underused Zen security feature can we leverage to a first class in our customers' data centers? And someone suggested VE, and then another one said, all right, hold my beer, and here we are. I'll talk a little bit, for those of you who haven't seen my other presentations, talk about our work. I'm going to explain what VE is for people who are not really connected to the x86 universe. I'll talk about the performance improvements that can be done with VE, our specific use case, and the state in Zen. So around 2014, we started pestering Andrew and Jan with some patches extending the existing VMI infrastructure. After many internal demos in 2015, we decided, okay, we can go ahead and try to build a security product. In 2016, we actually pushed something to our partners and got very encouraging feedback. And in 2017, we went all out with an actual release with the help of some very good people at Citrix. And using Citrix Zen Server 7.0, we made our security offering available to everyone that wants to try it. So what are virtualized exceptions, or HashV for short? They were presented by Ravi Sahita and Jun Nakajima. I'm hoping I'm pronouncing the name correctly. I'm sorry if I messed it up. In 2014, I think it was Chicago, it offered two use cases. One was for speeding up the networking operations in a virtual machine, and another one was right up our alley, speeding up introspection. Virtualized exceptions work hand in hand with VM-Func, or alt P2M in Zen. VM-Func showed up, I believe, in Haswell, and the last bit, virtualized exception, became part of the Broadwell microarchitecture. The thing with virtualized exceptions is that they allow converting exceptions that would normally trigger VM exits into simple guest interrupts, giving the ability to handle these exceptions in the context of a guest. It avoids a VM exit, which is pretty costly. It has quite some overhead. Currently, only EPT violations can be converted to virtualized exceptions. These exceptions use the previously unused vector 20. They require specifically enabling in VMCS, clearing a V bit in every paging structure, EPT paging structure of interest, and then the guest just sets an information area where the processor puts in details about the exception and implement the handler. So what are the performance opportunities for improvement here? Our VMI product relies heavily on EPT violations, and one of the things it does is monitor the page tables created inside the guest, and these page tables are the source of many such violations. Thousands of them per second during normal guest operation, even more when there's serious workload inside it. The design of our product is in such a way that the application, the security application, runs in a separate virtual machine, which obviously involves quite a path from the guest that triggers the event to the other VM that handles the violations. So right now, the code path appears quite fast. We've managed to get up to a 20% performance penalty, but obviously we're looking for something even better and believe VE, hash VE, is what can get us to below 10%. So what we plan to do with hash VE is pre-validate EPT violations and suppress those violations that are no interest to us, such as those triggered by AD bit flips, and the rest that are of importance convert to VM calls and send to the VM in which the security application runs. In our specific case, what we do is inject a tiny agent inside the guest, protected via EPT, make sure nothing inside the guest can touch it. Clone the IDT. We did this because on, for example, 64-bit Windows, there's this feature that periodically checks the integrity of the IDT. So putting in the handle for vector 20 would create quite a bug check. And so we clone it, we install the vector, we mark for VE the EPT entries that match the mapping for the guest page tables, the page tables set by the kernel for itself or for the applications. Handle or VE or virtualized exceptions that have a source as a source the flips of access dirty bits, and then pass to the VMI application, the actual security product, everything else, changes to the driver objects, possibly patches to the kernel code, who knows. These performance numbers have been gathered with an internal hypervisor we use to patch left and right every time we want to test a new technology. So for Google Chrome, it's not very clear here because the lines overlap, but the red line indicates all EPT violations triggered while Google Chrome runs, and the blue line that should be right beneath it represents the EPT violations that have been suppressed, EPT violations that we don't care about, just, as I said, AD bit flips. So in the specific case, the performance improvement is way above 50%. For Mozilla, the situation is a bit more complicated. It allocates a huge chunk of heap, which splits into even little smaller chunks. Each one of them can be executable or not. Apparently, the JavaScript engine uses it for just-in-time code generation. So it looks kind of wonky, but even with this, I'd say, unusual behavior, the V agent can reach almost 50% performance improvement. The current status in Zen, around Zen 4.6, or exactly in Zen 4.6, the initial alt pet2m and V code went into source tree. There have been several patches to alt pet2m fixing or improving things. And in 2017, we started looking very hard at using this feature. We extended, there are 2 patches currently on ZenDevel that are still being discussed. One of them plans to extend the function that hypercall that we added, setMemaccess multi, and simply adds a view ID that allows controlling the access bits for views other than the root one. And the other call, alt pet2m set suppress V, which controls the V bit from a separate domain other than the guest itself. There's a little bit of an issue here because the way Intel designed it, it allowed the guest to play with the V bit. And obviously, in our use case, having the guest interfere with it will be pretty bad. So we're still discussing of a way to satisfy both our needs and the use case that Intel had in mind. We, in 2018, early 2018, or hopefully the end of 2017, we plan to integrate it and maybe push it to our customers. I might be overly optimistic, but it's probably what got me here. And I think I've been doing pretty good with time. If you have any questions, I might not have the answer, but that's okay, it's just the way I like it. All right. Yes, it is injected inside the guest via the hypervisor by the security application.
Okay. For the purpose of the recording, so I'm going to ask them my question again. So the agent is inside the guest, right?
Yes.
So who ingests the agent?
The security application running a separate VM, which we call Security Virtual Appliance.
Thank you.
Okay, I could answer that one.
Okay.
All right. I think I'm done here.